start streaming. And I believe we're streaming live, so just do test again. Yep, we are. And okay, that's cool. And in particular, what we're going to do is we are going to jump away from this because I don't even know why I've got this open at the moment. Although actually, quick zoom in, control, and then zoom in like that. There we go. Top of the stack, Python programming. There we go. Go get the book. Since it's on there anyway, you might as well. Free advertising for myself. And we're going to go back. This is something that I came across. It was actually at the end of last week or over the weekend, so I thought I was just going to do a quick video on this, just because it's quite interesting, and I've just called it Mathematics in Python. And I managed to do this in like 25 lines of code, and somebody asked the question, and I don't know if I can get it typed out nicely here. I'll have a little go, possibly. But it was something like, let's see if I can, the best I can do for typing, but sine 1 over x, but actually let's multiply that by x and con x. So we've got x times sine 1 over x, and this is our function. So our function of x, which could be y for example, is equal to all of this that's in here. And actually, funny enough, this is quite interesting. I saw a question, and you're welcome to, like, or anyone that's actually watching this belatedly afterwards is welcome to put their little views on here. But is it easier reading code? Is it easier reading this function here? So let me draw on the screen here. So is it easier reading this, or actually easier reading the mathematics? Because some people actually, or at least I saw this posted by Professor somewhere, that it's actually easier reading, at least some people find it easier reading code, reading Python code, than they do reading the actual mathematics. And I think it's more for other parts of mathematics where the numbering or the nomenclature is different. But nevertheless, an interesting question. But let's just get back to, we've got this function of x that is equal to sine x, and it produces some kind of output, and it's kind of like, you know, what does it happen? At least in the question was actually, how does it behave close to 0, and is there, and what is the most interesting thing that you can ask about this question mark? And I actually don't know what the most interesting thing I can ask about this actually is. So interesting, because I can't move this across now. Let's just, I think I can drag and drop and stuff. There we go. So let's just sort of move it there. So that's basically it. Now we know what sine x looks like, and this is kind of like why I had to go to the drawing bits, because sine x looks something like this over here. I should choose a different color, so I'm just going to hit the undo button and a slightly thicker line, I guess, just so that we can see this. But sine x looks like this on my, like, oh, absolutely rubbish plot, but nevertheless it's good enough. And I wonder if I can brushes. There we go. Can we get, oh no, okay, shapes. So that's our axis. So let's just get, we'll draw an axis. So that's kind of like our, I'm just going to hit the undo button there again because I wanted the axis to be in blue. So sine x looks something like this, where it bobs up and down above the horizon. I haven't drawn this very well. And the graph of x, and this is kind of like how it should be asked. So sine x, I think sine x is 0 at 0, so that should be something like here. It's not the most amazing thing, but it crosses there, or, you know, one of these. So I'll move this one here. So that's sine x. So at 0, sine x equals 0, and then at 180 degrees and 270 degrees and 360 degrees, we get our peaks and our zeros and our troughs, our zeros and our peaks, and so forth, and it continues ad infinitum. And then the other chart that we would have, so we've dealt kind of like with one half of it, which is, so we've dealt with this, well, sorry, we've dealt with sine of x, but not sine of 1 over x. So we've got to do that next. And We can deal with this one quite simply because the graph of just x over here is just going to be this straight line. So the graph of y equals x is going to look something like this. And again, I'm going to hit undo and draw it in a different color just so that it's clear. But so this part here is going to look like that. Now we're going to get this multiplication of this green line and this red line, but actually we're looking at sine 1 over x. And one of the first questions that you have to ask when doing this is what actually happens. So let's just say now that, and this isn't a maths lesson, but A is, I'll go back to the normal colouring now, let's get back. We'll just say that A is equal to, and I have to probably go back to the line thickness as well, just to get it right. That'll be this one here, and that's fine. Okay, so we can say that A equals 1 over x like this, 1 over x. And then what happens to A? So what happens to A as x approaches 0? And what actually happens is this number gets smaller, so the denominator in the fraction, which is the x over here, is going to get smaller, and therefore A gets bigger. So kind of like our little answer there is A becomes large. In fact, it approaches infinity. Now, what is sine of 1 over x, or sine over 1 over x, when x is small, and therefore sine of a very, very large number, sine of infinity? And we don't know what sine of infinity is, but what we do know is that it lies in between the boundaries of plus and minus 1. So we can say, I believe, that, let's get just drawing a line again, so it'll be this line. But basically all of our sines lie so like in this boundary over here, so it's kind of like going to look like, if I can move it down a bit, this over here, copy and paste that down, and I didn't manage to copy and paste, so I wonder if I can, I'll just draw another line, but everything lies within these blue lines here. So now what we have is the product of this times by something, whatever this sine of this thing is, of this 1 over x, but we know that it lies within this boundary. So if you can kind of like imagine what this might look like now, for sure this point here is going to be at 0, and these points in the very close vicinity are going to be very close to the 0 as well. So it's kind of like some sort of sine of something. Now when x equals 1, we will have sine of 1 over 1, and if I can, I don't know if I got a scientific calculator here, or maybe I don't know. I don't even want to ruin the fun. Have I got sine there? No, I can go scientific trig. There we go. Okay, yes, I can do. So I'll just do escape here, and I'll just do 1, and then we'll take the trigonometry sine of 1, and that is. I think I'm not sure if that's 1 radian actually, so I've got to be careful about that. And really, in reality, well, it's just going to be, I think it's just going to be 1 degree, so sine of something very small, and we're going to get this very small number. So that's kind of like generally what's going to happen. So we're going to have this outward growing thing, and actually what I could do is, so let's get rid of that as well from there. What I could do is I could jump down and not actually run the code initially, but create another block of code, and I can do the import of a NumPy. It's taking its time, don't know why. Okay, there we go, import NumPy as NP. And then I don't have to import NumPy, I could have done import math, so I could have used the math module. There's loads of ways of getting sine, so import math, I could have done that as well. So I could have used this module, but I've used the NumPy module. So anyway, I can do np.sine like that, and then of any number that we want. And actually, just to get some help here, because I wonder if it does it, if it's going to do in radians, but it will have a description of what it is. So it is here, like, so x is a, okay, really like, an angle in radians, 2 over pi radians equals 360 degrees. That's our standard thing. So, but anyway, it's in radians. So this is like 1 radian. So it's like 1 part of 360th of a degree, I believe. We can actually print this out because we can just say that x is equal to that, and then we could sort of print x here, and we could see that we'll get some kind of smallish number. And I guess if we did like, if x was 10, because we could have gone back to our little chart here, we could inspect for a whole bunch of different numbers. But if x was, say, for example, 10 over here, or let's say x was a half, 0.5, let's go there and run it. We're going to get this number. But whatever number that we were to put in, I wonder actually if we could put in a whole series of numbers in here. I don't know if it will accept that. So 0.5 and 1, for example. Let's just see what happens if we get 2 things. Oh yeah, we do. We get an array back. That's quite cool. So I didn't know that you could do that. So you learn something every day. And I only knew that you could do that because it says x is array-like. So fantastic. So 0.75. Like run it again. But even if we put in a larger number, so like 10, 100, and so forth, we remember that we're going around the circle, that we're going to get these. Notice that, well, I was going to say that these are the same, but they're not exactly the same. But this array that's going to come back, so the sign of any of these angles in radians is always going to be between these boundaries, which is this blue over here up at the top, and this one over here, which is the plus and minus 1 points. So I should sort of like say it's bounded. The answer, the sign of 1 over x, it doesn't matter what x is going to lie in this range. And if I can get text out here, this is at the plus 1. I should move that a bit up. Let's just say it's over there. This is plus 1. And then this bit down here, if I do another one, it's going to be minus 1. So that's kind of like, that's what these blue lines represent. They're the plus and minus 1 on the y-axis effectively. So that's what we're going to get. And I guess also we could actually do this straight away, but we could say something like, we could use a NumPy range. Well, in fact, I do this anyway. So I might jump straight to the actual piece of code. So I've imported NumPy as NP. I didn't have to. I could have done. I wonder if I can actually do this straight away by math.sign there, and then hover over the sign over here and see. This doesn't take an array-like. So that's actually the difference between NumPy and the NumPy module and the math module. I think if I run this, it will throw an error. But let's have a look. Yeah, it does. Must be a real number and not a list. So I never knew what the difference was between them. NumPy is more powerful, is kind of like, the long and short of the answer. Oops. NP dot sign. So NumPy is slightly more powerful in that sense, because you could put in an array and get back an array back of all of the signs. So there we go. We've learned 2 things now. But anyway, let's continue from that. So we've got import NumPy as NP. We could have done math, but we've just realized, anyway, whatever, we could have done either. And then we're going to plot out a chart, and I just went for matplotlib.pyplot as PLT, but I think there was Plotly, which is quite nice, that I started using in a previous video. It's just a bit nicer because it prints it out onto a web page and you can zoom over it, but just for the purpose of keeping everything relatively simple, I've used matplotlib over here. And what I'm actually going to do just while I'm here is I'm going to hit the share button and copy this link. I'm just going to copy the link and I'm going to put it into what's known formally as Twitter. So I'll go on to Twitter, our Twitter app. Just going to post it in the link so that people can join. We are live now, and just post this link. I haven't been around for a while because I actually have been hospitalised, but I'm back and live. So we're now live, and just post it in. So let's just see what, if anyone does come in, they're welcome. You're welcome to ask questions, and you're welcome to put your views across as well. Anyway, so we've done our two imports, NumPy and Matplotlib. I'm doing this in a Jupyter notebook. I could have done it in the original code. In fact, I did do it in the original code, and I did it in the, I can't remember what you call it over here now, the interactive session in VS Code, but it's quite nice sometimes just using the Jupyter notebook that's embedded in it. So the first thing to do is write this function, and kind of like just going back originally to the original bit, we've got this function which is x times by sine of 1 over x, and the original, as somebody pointed out, which is, sometimes this is actually Python code is actually easier to read sometimes than this, and I do see why, because sometimes when you've got brackets and things, and if you've got a sum of something from I equals 0 to infinity, what is inside the sum and outside of the sum, and how do you rigorously write it? Whereas when it comes to computational stuff, it's you can use brackets basically, and at least you have to make it very clear to the interpreter, and there's only kind of like one given way of doing it. So without arguments or discussion between parties, but anyway, everyone will have their view on that. But we've got this function of x, so x goes in there, and what we're going to return back is x times by the sine of 1 over x, just like this. So that's what we're going to get back. Now, the nice thing about using NumPy is, and I could have done this, and actually when I first did this, I started doing it in lists, and I was like, well, lists they're okay. But what I want to do is get a bunch of x values, really, and then a bunch of y values, and then plot those out. So I actually wanted to do, I wonder if I can do a new paint. Oops, didn't do that right. Get rid of that. Paint. There we go, our painting app. So I get a new one open. But basically, over here, I want something like to create this table. So it will look something like this. I'm going to create a table over here. And this is pretty standard old school stuff. Bitcoin just traded, that's what that noise was. And I'll put in an x over. Let's just get our text. Yeah, there we go. So these are our x values over here. Let's just make that big, because otherwise it's unreadable. So 28. Let's make it big. So these are our x values over here, and these are our y values, but what we're actually calling our function of x, which is just basically the result. So we want to put in just a whole bunch of things that go something like this, if I can order them properly, but basically something like 0, 0.1. Oops, okay, fine, if I make this a tiny bit wider, because it won't take it. But basically 0.1. In fact, we start from something negative, so like minus 1, and then minus 0.9, and then 0.9, and then minus 0.8, so forth. Let's continue down, we keep continuing down. Right, let's just go. Don't know why that doesn't any more dots there, but let's just continue, and I'll move this across a little bit. So it's beginning to look something like this, and then finally we're going to have why are my numbers right? 0.9 there, and then finally we're going to get 1 over here, 1.0. So something like this. We've got this our little thing over here with some dots in the middle. That is our x values, and then corresponding to our x values, we're going to have a bunch of y values, whatever they are, for our function of x. So we're basically going to make this table here. So we might have like 100, 200, we don't know what's coming out of here, 300, so forth, ... So continue, and then 500. I still don't get why that does that. 500, let's just do it like that. And 600. So something like that. For every value of x, over here we've got a value of our function of x, whatever it spits out. So like, you know, whatever these are, they translate, so this one goes to that one and so forth. Like however we want to look at it, we've created this like useful little table. And the reason why I was drawing all of that is that NumPy lets us do that quite conveniently. So if I just drag that over to the side, NumPy has this little function over here, which is the arrange function, and it's got a start and a stop, very similar to the list function, but it's got one convenient thing, that its step size isn't in integer increments. Now you could do a list, have a step size in integer increments, but in fact I want to just test that out because I want to be careful that I don't say the wrong thing. But let's just do this. X equals, because our standard range function will look something like this: range 0, 10, 0.1, and then do something like for I in X, print out the value of X like that, and I think that should be enough sufficient to iterate through. And as a float object can't be interpreted as an integer, and I think it's to do with that basically, which is the step size, which is 1, and then it could, so then, oh actually hold on, I've got to be very careful of that. I've probably got to do this actually, take that there, for I in that, and that's probably what I meant, which is the 0.1 like this. Just get rid of this, don't need that X over there, and then print I like that. If we run it, we get that error, and I think now if I run that, yeah, we do. We get the integer parts of it, and then you'd have to do some sort of trick. Like, you know, it's not like the world's hardest trick to do, but if you wanted to get like a fractional bit, you'd have to do print I over that, and then you could get the fractional parts. But what it wouldn't let you do is a fractional step size, and NumPy gives you this flexibility. This NP arrange gives you this flexibility. Now we could go from -10 to 10 here like this, so that's perfectly allowable. We just go from -10 all the way to 10. So we've got like 20 items in here, each of increment 1 over 10, so 1/10. So we could manufacture something like that, but the NumPy gives us a slightly better version of that. So if I actually, I'll just comment this one out. But basically what we've done here is we've got, in fact, NP, because it's already nothing, dot range. Oops, I spelled this wrong because I look for the IntelliSense, because the IntelliSense kind of like gives us, it tells us that we're on the right track. It avoids all spelling mistakes. Now we can do the same for -10 and then to 10, and then, but more instead of that, now we can do this much more conveniently, because we can go -1 to 1. Then we can say that our step size, and I actually explicitly say step because it's clear, but you don't have to. You can actually just say 0.1 because that's how it basically works. And then for I in range, or for I in this, I wonder if I can actually do that. I can then print, I wonder if that gives exactly the same thing, but that's basically for each item in the NumPy array. The one thing about it, actually, looking at this here, is you get this floating point error, which is really, really annoying, actually. It doesn't have much bearing on what we do, but still kind of like, it is just very annoying that it's there. I think there's a way of sort of rounding it out, getting rid of the floating point error, which I might try to do at some point in time. But that defeats the purpose. What we do know is that we've got a whole set of numbers. But more, I think more to the point is, if I did, let's just get rid of that now. If I just did the same, that basically X is equal to this NumPy array, and then just print and then do the value of X, it transfers into this. But again, I guess it's because it's, well, because I wonder if you can actually state here, so I'm going to say step equals, and then I wonder if there's yeah, there is a D type, and then I guess I don't know what the D types, how they work out, but something like np.int. There we go. That might be a bit cleaner. That might get rid of the actual little parts of it. I want actually dot, I think is it float, like a small floating number that doesn't occupy too much memory, so something like that maybe. I wonder if that will be a bit cleaner. Not sure, but anyway, what we are going to get is this long list. We're going to get this list of numbers sequentially, and so we're going to get our list of x's over here, and then we're going to create a list of y's afterwards. But we say that y's is np.zeros like, which is just basically we're arranging it to be of the same size effectively as the x's. Otherwise we'd be like missing one element. So you can imagine that, like, I don't know, if you miss some elements here, that every function of x now doesn't have a corresponding value of x, and that wouldn't kind of like work for the purpose of plotting a chart out. So that's what the zeros like does, and actually if I hover over it, you can kind of like see that, which is return an array of zeros with the same shape and type as a given array. So, and we're just saying give it the same shape as the x values, and then we're going to populate it. So we say for iv in enumerate x values, and the I is the index part of it, and the v is the actual value part of it. So go through each one, and the reason we do that is because we want to actually assign our values afterwards to the index of the array. And also we've got to remember that arrays start at 0. I say that nearly every time that we do arrays, but we just got to remember that the first element of the array is 0. So if I was to, well, I can actually just write straight on this over here, but this is, I don't actually have to write down this left hand side, I can write anywhere really, so let's move it across a bit. I can drag that across, there we go. But this is the 0th index, and this is index 1, and this is index 2. I'll colour them all in a different colour, but these are our indices basically. And then dot dot dot, and then this is index 3 and 4 and so forth. And if I just pull it up, so that's basically how all or most languages, I think there's 1 or 2 languages that don't start with index 0, but that points to that effectively. I won't do it like that. I can get an arrow there, but this one sort of like points over to there and so forth. So copy that, and well, I can't copy and paste it, but we get the idea that each one of these, this is index 0, this is index 1, this is index 2, and so forth. That's how arrays work, just in general in Python and in most languages. So move it off there. So we're going to go through our each value, and we're going to run our function on every value of x. That's what we're going to do, and we're going to start from just to keep it symmetric, I've actually put in a boundary, and I've said whatever value, you can pump in any number, and I'm going to play around with these numbers afterwards. But whatever number this is, start from a negative point and sort of like go over to the positive side of it, and in steps of 0.1. I could have done other steps. And finally, for the purpose of the plot, all we need to do is plot the x values and the y values. We can say that we've got x values here, so I'll say x values over here, and our y values will go over there on the y-axis, and we've got a nice little title in the plot.show, and we can actually run this now. So that's basically everything. And there we go, we get this, and that we need to actually play with this, because our boundary over here, but this is interesting because this is what comes about, but what actually does come about, I sort of draw it because we will zoom in afterwards on it, but what we've got here is this: we're centered around this bit, and it does look a little bit exaggerated, but the asymptotes over here are 1, and there'd be a -1 down here as well, but we haven't managed to capture that. But maybe with a little bit of zooming we can, so we can play around with that. So I just make this a bit smaller, and we start off with a 1, and we see that it looks like this now. We've got a bit more of a behavioural thing, but actually we never get to the -1 point, even though that we know that we're bounded. And that, I suppose, is because well, the sine of 1 over x never really reaches that, I guess. So if I was to pull this one up again, not this one, but this one over here, what we actually need to do is, well, what would be quite interesting is just to print out sine 1 over x, and I actually did that initially. So I'm going to do a little cheat here. In fact, I can do this. A couple of ways of doing it, but just before we return that, I'll stick that in there, stick that return in. See, the other one gets greyed out anyway. But this is what sine 1 over x will look like now, which is like that. And we can see that it goes from the -1 to the +1, but we've now got to multiply that by our value of x, and our value of x never really, I guess, our value of x here, because we can also print this out. So return just x. Now that's just going to be should just be a straight line, right? So that's our straight line that comes out here, but we don't want to do that because that's rather boring. That's our sine of 1 over x, and that's what sine of 1 over x looks like, apart from, I guess, at this point where x equals 0, where we start having some sort of problem because sine 1 over x. But what's happening is our frequency is actually changing. I think that's the one takeout of this, is that the lines are getting compressed closer to each other. So I'm talking about the difference between the peaks, which is here and here. So this kind of like width compared to the next peaks or troughs is kind of like, if I was to draw it somewhere else, these ones are slightly more inward over here. That's our next peak to trough, and our next one, and so forth. So they get closer and closer, and that's what the 1 over x is actually doing to our function. So let's just go back here, and we'll comment this one out too, and get back to our original function. And that's kind of like effectively what it looks like, and we can sort of like inspect it and go a little bit closer in, so we don't have to go from 1, but we can go from 0.5, for example, over here like that. And now that's what it looks like, and that's effectively the behavior of our function. But let's just go a little bit more in. I wonder if we can do it to like 0.2. There we go. We still get interesting. I wonder if we do get an oddity. No, it looks relatively okay. Boundary there. I might have to put in some more dot decimals in this so that it looks better like that. Just because as we go in here, and actually what I did somewhere, I think I would have done this, but this step size is just going to be, we'll just say boundary divided by 100. That means that now we only have to put in one number conveniently to get our lower bound, which is negative of that number, our upper bound, which is just that number, and then our step size. So we want sort of like enough numbers of steps inside of that to actually plot it quite nice. And that's kind of like what this little chart looks like. So that's sort of like just some mathematics in Python. You could do your investigations, and you could do mathematics outside of a programming language. But that's kind of like how it looks like in Python, and what you can do, and sort of like the capability and the power, and the fact that you can muck around with it quite quickly. And all of this only ever really costed us not even 25 lines of code. So I think I might stop here. That's kind of like enough for this little video. This is mathematics in Python. Welcome to copy, but put your questions and so forth. If you do have any questions, definitely post them. If you have any comments, post them. And also, like, I keep forgetting to do this, so I should say, if you like the video, if you found it interesting, hit the like button, hit the follow button, hit the subscribe button, because it's helpful to have people follow. And yeah, your views and comments as well are welcome. And that's it. So that's some simple mathematics in Python.